Hi everyone, today we'll be discussing the LeetCode problem of the day, swim in rising water. You are given an n cross n integer matrix grid where each value, grid ij, represents the elevation at that point. That means you have an infinite land and in that you have an elevation grid of size n cross n. And these each cell has a elevation 0, 2, 1, 3. So now it says it starts raining and the water gradually rises over time, and at time t the water level is t, and meaning any cell with elevation less than equal to t is submerged or reachable. So that means initially the water level is 0, so you can only reach this cell. At t equal to 1 the water level of the ground reaches height 1. That means you can also reach this cell because the water level is 1. And at t equal to 2 you can reach this cell as well, and at t equal to 3 even this cell is reachable, or this cell is also submerged. And next he says that you can swim from a square to another four directionally adjacent square if and only if the elevation of both squares is at most t. So that means if you're at a square, you can swim at any four directions. And if your current value is 3, and suppose the adjacent square value is 5, so you can swim from 3 to 5 only if the water level is greater than equal to 5. Otherwise, you can't climb the stairs. You can swim only if the water level is greater than equal to 5. If you see that if the water level is greater than equal to 5, then both of these are submerged in water. So you can simply swim from this point to this point. And similarly, if you have an adjacent neighbor which is less than this, here also you can't simply jump from 3 to 1. You can only swim from 3 to 1 if the water level is greater than equal to 3. That means it is greater than equal to the maximum of both of these. And it says that you can swim infinite distance in 0 time, and you must always stay in the boundaries of this grid. And at the end you just have to return the minimum time. At minimum time you can reach from the starting point 0, 0 to the ending point n minus 1, n minus 1. So if you see the first example, let me just erase this. Yeah, in the first example, you're initially here at 0, 0 and t equal to 0. So at t equal to 0, you can't go anywhere because all the adjacent values are greater, so you can't swim there. So at t equal to 1, you can move to the bottom cell. I mean, you can swim from here to here because this cell is also submerged. And from here you can't go anywhere because 3 is higher and it's not submerged yet. Now at t equal to 2, from here you can again swim back, and you can also swim to the right. So that's what he mentioned. From here you can swim here in 0 time. That means you can swim really fast. So at t equal to 2, even this cell is submerged, so you can swim here as well. Now at t equal to 3, even the bottom cell is submerged, so you can swim here. So it requires at least 3 seconds to reach the bottom cell, so the answer is 3. So it is true that even at t equal to 20, we can reach from here to here because all the cells are submerged, but we want to return the minimum time in which you can reach from 0, 0 to n minus 1, n minus 1. So the output is 3. Now if we quickly see the second input, here initially you're at 0, 0 and t equal to 0. So at t equal to 1, you can swim here, then at t equal to 2 you can go here, then 3, then 4, and then 5. Now here at t equal to 6 you can see that this end cell is also submerged, but you can't reach here yet because here you have the greater values. So currently t equal to 6, but you are stuck at this cell only. You are stuck at this cell until the value of t reaches 16, because in all these paths these values are all greater, so this is the only least value after this. So at t equal to 16 you can go here, and since this 15 is also less than 16 you can go here and all this way. So you can swim, and at this point you will stop. I don't know, at this point also you can swim bottom, because 10 is also less than 16, so 10 is also submerged, and then you can swim in this path, and finally you can reach 6. So at t equal to 16 you are able to reach 6, so this is the minimum time in which you are able to reach the bottom cell. Now let's go with the approach. So to reach the bottom cell from the top cell, we are following this path, and in this path the maximum height is 16. So at t equal to 16 you are able to reach the cell 6. So we can say that to reach the cell 6 the minimum height needed is 16. So to solve this we can think of Dijkstra algorithm, which is used to find the shortest path from single source to all possible cells. So we can see that from this source we can reach 6 in this path also, but in this path the maximum value is 24. So if we use the Dijkstra algorithm, it will find the shortest path needed to reach a particular cell. So we are interested in this cell, so this is the path we take. Now let's go over the implementation of this algorithm. So initially we'll take a height array, and all the heights are infinite. So that means you can't reach any of the height so far, because it takes infinite time to reach that. So initially you're starting at this cell. So what you can do is you can mark this as the height of this cell, which is 0. So that means at t equal to 0 you're able to reach this cell from this cell, because you're starting here. Now when you will add this cell in the priority queue, because you want to find the shortest path. So we'll maintain a priority queue. In the priority queue you will first add this cell 0, and you will start the iteration. Now when you pop this 0, from this 0 you can travel in all 4 directions, top, left, bottom, right, but top and left are going out of bound, so you can only go to the right and to the bottom. So now if you want to go to the right, we have the condition that the maximum of both of these values should be, the water level should be at least equal to the maximum of both of them. So we can say that max of the grid of current and grid of neighbor. Let me make this brackets. So the maximum of both of them, if it's less than equal to the height of neighbor. Let me just move this. So the maximum of the grid, the current value and the neighbor value, if it's less than the height of the neighbor, which is initially infinite. So that means in the in t equal to 1 you are able to reach this cell. So this cell value will be equal to the max of these both. So the infinite value you will replace with 1, and once you are doing this, you will add this in your priority queue as well. 0, it will be popped because we are just removing it. So the first neighbor is 1, we have updated and added in our priority queue, and the next neighbor is 24. So for 24 also, the maximum of current and the neighbor is 24, and that is less than equal to the infinite value. So we will update the height to be 24. So that means you are able to reach this cell if the time is equal to 24, and you will also add 24 in your priority queue. Now all the neighbors are done, so you'll move to the next element in the priority queue, which is 1. So now we will pop the 1 and you'll check the neighbors. So 1's neighbor is 0, 2 and 23. Now if you want to check for 0, the maximum of current and the neighbor is 1, and 1 is less than height of neighbor. Height of neighbor is already 0, so it is already less than the max value, so you won't travel to this again. You will travel to the neighbor only if the neighbor value is greater, so that we'll try to minimize, make it smaller. So since the height is already smaller, you won't go here. So you'll go to the 2 and you'll update the value from infinite to 2 and add it in your priority queue. Similarly, from 1 you can go to 23. You will add 23 as well. So here it will be 23. And next you are at 2. From 2 you can go to 3, you can go to 22. So you will pop the 2, you will add 3, you will also add 22. And let me also update these values, 3 and 22, sorry. And now you will pop the 3, and from the 3 its neighbors are 4 and 24. So you will add 4. Okay, neighbors are 4 and 21. So you'll add 4, you'll add 21, and also update the height values, 4 and then 21. Okay, now the top value is 4, so you will pop the 4, and the neighbors are 5 and 3. So for 3 again, the max of the grid, the current and the neighbor is 4, but the height is 3. So this is false, so you won't add the 3. So you will only add the 5. So 5 is added, and this is updated to 5. So now we can see, to have a better visualization, I want to change the value of this from 24 to 14. So this will be 14, and this will be 14 as well. Yeah. So now the top of the priority queue is 5. So we will pop the 5 and we'll check the neighbors. The neighbors are 21, 4 and 16. 4 is already included. So we will, and 21 is also added. So we'll just add the 16 while we update the value to 16. Yeah, so now we can see that the top of the priority queue will be 14, because currently 14 is the smallest value and not 16, because we updated the value to 14. So 14 will be the smallest, so we will pop the 14. So when we pop the 14, we can see that the neighbors are 0, 23 and 12. So here is the important part. So max of current and the neighbor, max of 14 and 0 is 14, and 14 less than height of neighbor is 0. So 14 less than 0 is false, so we won't update this. But if we see this 23, here also I think max of current and neighbor is 23, and the height is also 23. So previously it was infinite, we updated it to 23, but now also to reach this, either we take this path or we take this path, we need 23. So that's why we won't update it again. So we won't update 23 as well, and we'll move to the next neighbor. So for 14, the next neighbor is 12. So for 12, we can see that max of 14 and 12 is 14, and this 14 is less than the infinite value. So you'll update here as 14. Notice that you will update the distance as max of current and the neighbor, not just the value. You will update the max of both of the values in this height. So once this is updated, you will add it in your priority queue. So it will be 14, and this 14 is representing this element. Now next step is you'll pop it and you'll check the neighbors. So neighbors are 13 and 11. So 13 and 11. But to reach 13, you need the height at least 14. So you will add 14 only in your height map, 14 and 14. And you'll add both of the 14s in your priority queue. 114 is representing this 11, and 114 is representing 13. Now when we pop it, suppose we are popping this one. So we pop 14, and we will add the neighbors. One is 17, one is 10. So the max of 14 and 17 is 17. So here we will add 17. And max of 14 and 10 is 14. So here also we'll add 14. So similarly, we'll just continue the loop. So this will be 14, and this will be 14. This also 14. And at the end, this also reaches 14. But once you reach the bottom cell, you can simply break the loop and you can simply return the value. Because since we are doing a Dijkstra algorithm, the first time you reach the bottom cell, that will be the shortest path. So as soon as you reach the bottom cell, you can just return the height value. Now let's quickly go over the code and it will be a bit more clear. So first let me take the size of the grid. I think it's a square, yeah, n cross n. So we just need to take n. And let me create a height array. New int n. And initially I want to fill all the values with the max value, infinite value. Less than n plus plus. Arrays dot fill height of I. The value will be integer dot max value. So once this is filled, we know that since we are starting at the 0 0, we can fill the height of 0 0 equal to grid of 0 0. So if the value of grid is 3, so only at time equal to 3 you can start swimming from this cell. So once this is filled, we'll also initialize a priority queue. In the priority queue, I want to add the value of the element as well as the index. So I can take an array for that. Suppose if I want to add this element, it will look like 23 and row equal to 1, column equal to 1. So this array will be added for this element. So the type will be integer array. We can also create a class, but this will be a bit quicker. PQ priority queue. And to compare it, so we can use a shorthand method. We have A and B, and this will be compared by integer dot compare A of 0 and B of 0, because the first index of the array will contain the value and the next indexes will contain the row and the column values. So this priority queue will be given priority based on the value. So once the priority queue is created, let me just add the first element. New int value will be grid of 0 0, and row will be 0, column will be 0. Now we'll just iterate on the priority queue while it is not equal to empty. Top equal to pq.remove. So once we get the top value, let's just extract the values from it. Let's say row equal to top of 1, column equal to top of 2, value equal to top of 0. So once we got the top element, we need to check all the neighbors. So each element have 4 neighbors, top, left, bottom, right. So for that we can just create a direction array to quickly iterate on that. Int okay, we'll initialize with values. So again we can move top, bottom, right and left. So if you want to move to the top, row is -1, column is 0. If you want to go to the bottom, row 1, column 0. Now to go to the left, row remains 0 but column is -1, and to go to the right, row 0, column is +1. So now we can just iterate on this direction array. I less than 4 x equal to row plus directions of I 0. Similarly, we can have y equal to column plus directions of I and 1. Now once you have the row and column, these values can also go out of the grid, because if you're at 4, if you go to the right or if you go to the top, it will go out of the grid. So first we need to check if the values are in the grid or not. X, y and n. So let's just first fill the check function. Boolean check int x, int y, int n. Return x should be greater than or equal to 0 and y should be greater than or equal to 0, and x should be less than n and y should be less than n. If all of it is true, then we return true. Otherwise, even if one of it is false, this entire thing will return false. So if the check is true, and now we see math.max, the current value is value and the grid value is grid of x and y. If max of value and the grid is less than height of x and y, so we find a better height, so we can just update our height of xy equal to this value, math.max, current value and the neighbor value. And once we do it, we also need to add this in our priority queue. New int values will be height of x and y, row is x, column is y, and then at the end return height of n-1, n-1. Also, at the first time when we find the height, when we reach the last cell, we can directly return it there itself, so that it will save us some iterations. So if x equal to n-1 and y equal to n-1, then we can simply return this. So let me test it and submit. Yeah, it works. Finally, let's do the time and space complexity analysis. So for the time complexity, since we are we will be iterating on all these cells, and for each cell we will push it in the priority queue, and also at some point we will pop it, and push pop operation will take log time. So total we have n into n log n to n. So this is the time complexity. For space complexity, we are just creating a height 2D array of size n cross n, and also this priority queue. So space complexity will be order of n square. N square. We can also have this as n square log n square. And I also have the code in Python if anyone wants to view it. I'll add it in the description as well. And let's catch up in the next video.